All right, so the question was asked about the idea of a null and alternative seems kind of simple. Why does the book have to restate it so many times in so many different ways? And the reason, I guess, is there are just so many things that we can question in life, and the way we ask those questions is different all the time because a lot of reasons. The situation's different, but it's also a difference in perspective. So let's just talk about null hypothesis. There we go. So this is chapter 4 we're working on here. Hypothesis tests. Oops. Order. And so far we've played around with sections 4.1 and 4.2. We're going to throw 4.3, 2, 3, and 4 in today. 4.2 isn't much of a jump from what we did last time. 4.3 is a big jump. So I'll have to look at that a little bit. So the idea of a null hypothesis versus the alternative. And null hypothesis is often some prior knowledge. And the alternative hypothesis is often some new theory that we're going to test against that prior knowledge. Often it comes from somebody asking a question, wondering about something, or seeing something and say, hey, that seems unusual compared to what I knew. And the idea of what is unusual compared to other prior knowledge and what isn't is a subjective thing. So that's another thing we're trying to wrap our minds around. What is unusual compared to what is expected? And we've made an attempt at quantifying this since the beginning of the course. In like week 2, we talked about this 95% rule that relates to 2 standard deviation to try and identify outliers. When is something unusual compared to the rest of the group? Like body temperature. Man, your temperature is unusually high. Is that normal or is something wrong? Or we change something, like I start biking more. Will my sleep improve if I start getting more exercise because I haven't been sleeping well? So all these different questions we can ask, and then after we can say, okay, did it make a difference? And then how do we measure that difference is what we're trying to look at here. And the book, I think, restates this idea of a null and alternative so many times in so many different ways, just because there's so much variety out there in life. But there is this basic idea, this idea of prior knowledge and this new knowledge or theory that we try to test against it. So I don't know if that completely answers your question, Tammy, but that's kind of like the theme of hypothesis tests. And given that every situation is different, we just kind of got to look at a lot of different examples to wrap our minds around it. So I've been looking at hypothesis tests since I guess I started in college, and we all kind of ask these things naturally in our lives and then try and intuitively answer them. So in some sense, we've all been doing hypothesis tests since we were born, really. But this quantification of it is the hard part. So let's look at some more examples of it. And so I have a ton of different ones to look at here. I think I'm going to start with this one about a survey you guys did for me in the beginning of the quarter. So there was that syllabus quiz to say, hey, did you read the syllabus, about the policies? And the last question was, hey, how much TV on average do you watch each day? And by TV, that's kind of an antiquated term now, but it's, television, talk and see, screen time where you're watching something. Like maybe you're playing a video game, maybe you're binging on Netflix, maybe you're doing YouTube. The new thing is my daughters are addictive to, what's that, TikTok. right? They're walking around the house staring at these TikToks on their screen. And so screen time is what I was kind of aiming at with this right here. And we've got a bit of diversity here in the data. And I'm going to share this out with everybody. And we're going to put this into StatKey to play around with it. So remember, when we share something from Google, we want to make sure the link is available to everyone. So I need to update this one. And when I make something new, it depends on your account, it's often restricted. So copy, let's go to chat, what's going on there? You feel like an outlier. Oh, interesting. I don't know if that makes you an outlier. I know lots of people that do that. Even my kids, they watch some interesting things on TikTok and say, hey, Dad, check this out. You know you can do that? And once in a while, I'm like, I don't need to see that again. Sometimes it is interesting. And my wife's really into health stuff, and she fortunately prompts me to do healthy things too. All right, so let's see, I was about to share this. Yes, right, so doing other things at the same time, multitasking, that's kind of interesting too. So this is TV hours from our class there, if you want to grab the data and check it out. So what I'm going to do is I'm going to take this, I'm going to put it in StatKey and just see what it looks like. So copy it, find myself a new StatKey page here. Let's put you there. And I go to StatKey so much lately, Google says, hey, here you go, check it out. Podcasts. Oh, cool. Yeah, you know, there's a lot of podcasts I want to check out, and I need to. I discovered one the other day called The Hidden Brain that I want to look at more of. It was the last one I heard an advertisement for was like how hard communication is. Why, when we say something to somebody, do they not quite understand what we meant, and how can we make that better? Which is something I've struggled with all my life, especially because I'm trying to be a teacher. All right, so let's see. First thing I want to do is I just want to take a quick look at what this data looks like. So I'm going to jump into StatKey. And I'll get rid of that link too if you want to go there. And if the data isn't already in StatKey, then I can't share it with you. So I have to share the data separate so that we can all put it in StatKey. And ultimately what we're going to do is we're going to do a hypothesis test with this data. But I want to see a pretty histogram here. So let's get rid of mammal longevity. Oh, got the wrong one. Between data, copy, StatKey, paste. Okay, so I think I have a header, but I don't have a first column. Okay, so here's the data as a dot plot. Let's look at it as a histogram. So it's a bit skewed right. There's a few people who seem to watch a bit more TV than others, screen time than others, but it looks like most of the class is between 1 and 4 hours of TV per day. Box plot shows that person that did 10 hours is unusual compared to the rest of the group. So we have that 1.5 IQR rule, which is what StatKey is applying here. They don't show the 2 standard deviation rule. Unfortunately, we have to go to a spreadsheet and calculate that out. But I'm not really worried about that. What I'm wondering is, how does our statistics class compare to like US adults as a whole? And I looked that up earlier, and the latest stats are, on average, US adults watch about 4.5 hours per day of TV stuff. 4 hours per day is the US average. So I'm gonna write down my, my hypothesis, my population, my parameter, my sample, statistic, all that stuff. So I'm wondering, do BMCC statistics students watch less TV than most adults? Okay, so question there then, okay, what is my population? Well, although I'm comparing to all adults, really my population here is BMCC statistics students. I might be able to generalize that to BMCC students. And one thing that's questionable with either population is this ain't a random sample, right? It's very convenient. I just said, hey, you guys right there, you guys stop, tell me what you think. So this isn't a good sample, but we're gonna do it anyway. So I'm gonna go for a population here of BMCC students, BMCC statistics students. So population in question. BMCC stat students. And that's, oh, when somebody presents data, I always have to stop and think, who are they talking about here? Am I in this group, right? Oh, parameter. For the parameter, I'm going to use the mean TV hours per day. Remember, population means get the symbol mu. So that's my mu there. And then I have this sample of how many students, again, responded to that question. 40 students responded to this question. I think there's 43. Where did it go? Sample. 40 MCC stat students. And my statistic is their mean. So mean TV hours per day. That would be called X bar because it's a sample mean. And what did StatKey say about that? StatKey said the mean was 2.831 hours. And let's see. Technically, I don't think I need that third decimal point. The typical rounding rule, oh, I do, somebody gave me 1.25. The typical rounding rule is to go one more decimal than the data showed. So this data has a 0.25 in there. So yeah, I gotta use all three. Oops, that doesn't matter. Back here, so 2.831. 2.831, oh gosh, sorry. Hours per day. And I guess I should have written the national mean I looked up, which was said to be, oh, I didn't know I could do that. Escape, click. Oh, how do I undo that? There we go. It's 4.5 hours per day. Okay, so it's always a good idea to make sure, do you understand what the population is? You're looking at what parameter you're testing, and then we go on to talk about the hypotheses. So I have this question up here. Do BMCC statistics students watch less? Okay, so less, that's pretty straightforward. That's a less than. Since there's not an equal sign there, then it's got to be the alternative hypothesis. Now, the null hypothesis is a tricky one. There isn't agreement in the world of statistics about what your null hypothesis should be compared to the alternative. There's two groups of people out there in the way they think about it. So the authors of our textbook, and I'm kind of in their camp, they think that the null hypothesis should always be an equal to. That's it, just an equal to. Sorry about that. The alternative is pretty straightforward here. That's just the question that was asked. So HA, the alternative hypothesis, that's going to be that mu is less than 4.5. Now, there is another group of statistics people out there who think if the alternative was given as, the claim was given as a less than 4.5, then their belief is that the null hypothesis should be the opposite of that, and the opposite of less than would be greater than or equal to. So the homework questions that I assigned to you are from a system that lots of teachers write problems for, writing problems that have some change in the parameters is challenging. So I don't have the time or means to write a whole new set of questions for a class. So I borrow questions from lots of other teachers. And you'll see sometimes in the homework, they'll say the null hypothesis is an equal to. And other times you'll see it's something like a greater than or equal to. From what I've noticed in our book, I've never seen them use this notation. But the book I used last year jumped back and forth between these. So it's not a huge deal. Bottom line is, when you're choosing your null and alternative hypothesis, remember the alternative cannot have an equal sign. And I'm just going to put a little note about that. So this idea of which one's the null, that's not really a big deal. The alternative is a big deal. So just a reminder, the alternative, I'll explain why this is now. I didn't explain it last class. The alternative may not have an equals in it. So possible alternatives are less than or greater than or not equal. That's okay, right? That's not an equal sign. It's a not equal sign. An alternative cannot have a greater than or equal to or a less than or equal to. And the reason is, in statistics, we can never prove that something is true. All we can say is that there is evidence to support it. Evidence. And do I have all of the evidence? The answer is never. So I can never for sure in statistics identify something to be absolutely 100% correct. That is impossible. I cannot say the average amount of TV watched is exactly 4.5 hours. If we go to the data source, we'll find that they have a margin of error on that, okay? So in statistics, when we're talking about samples to predict things about a population, confidence intervals, and hypothesis tests, we never know something is exactly a single number. We can say it's a range of numbers. We can say the data supports that it's bigger than some number, but we can never say this is exactly a single number. It's not possible. So the alternative is something we're usually trying to find evidence for. So that's a goal and hypothesis test. We are looking for evidence of this. And either we can say the evidence exists to support it, or the evidence doesn't exist. So it's kind of like, you know, if you have to go to trial for something and they say, well, you're innocent until proven guilty, we have to find enough evidence to support guilt. Otherwise, if there's not quite enough evidence, there's only a little evidence, we got to say, I guess you're not guilty. Now, does not guilty really mean you're innocent? Not necessarily. Okay, so this is kind of related to that idea. All right, so kind of some general ideas again about the hypothesis test. The alternative cannot have an equal sign in it. So you have 3 choices for an alternative, and we figure that out by looking at the question or claim that's involved. All right, so I have my null and alternative hypothesis. Next thing I want to do is take the data and run my test. So to do that, if we're doing a mean, we have to have the original data source. And for those of you who joined late, I'm going to re-share that in case you want to run this test too. Google share link. And again, I had to double check that that's everyone. Yep. So this is the TV data. And for those of you who are wondering why I'm sharing it again, the way the way Zoom chat works is if you join the meeting later, you don't see the previous chat stuff. So for anyone that just recently joined, that's the link to this data here. And what I need to do is I need to copy it and put it in a StatKey to run the test. So I'm going to highlight the title all the way down to the bottom, copy, and then go find my StatKey here. So earlier I plugged it in the StatKey just to take a look at what the data looked like. So again, here's the box plot. National average is 4.5, which is somewhere in the 4th quarter of this data. So at least 75% of you don't watch as much as the national average. The mean is definitely less than the national average, but we've got this spread of 2, right? So what does that mean? If we look at the mean and the standard deviation, the mean is about 3, the standard deviation is about 2. So that means most people in this class watch somewhere between 1 and 5 hours of TV per day is what the mean and the standard deviation tell me. So based on this sample, is the national average kind of in the sample? Yeah, it's out to the right, but it's in there. Next thing we're going to do is we're going to take this data and run a hypothesis test for a single mean. So I'm at StatKey here, and I'm going over to hypothesis test for a single mean. And I have to paste my data in here, replace whatever's there. So I went to edit data, paste, and double check. Do I have a header row? Yes, but I don't have identifiers. Okay. If you're not sure what page I'm at in StatKey, here is a link in the chat. This is hypothesis test mean. All right. So a couple things to do once you're in StatKey. Number one, get your data in there, and edit data is easier than upload file. Just copy and paste it in there. Once that's in there, then you have to adjust the null hypothesis. And it doesn't matter whether your null hypothesis was an equal to or a greater than or equal to. StatKey always says equal to. So just go here and plug in your number. That would be the population data, which is the 4.5, not the sample data. Very important. Null hypothesis tests are centered around the prior knowledge. We assume the prior knowledge is true to start. Okay, so I have null hypothesis, sample data, generate. In some notes I write, I say use at least 5,000 resamples. Sometimes I say at least 6,000. Use thousands, not a huge deal. I'm gonna go for 7,000 today. All right, so next thing I have to do is think about what do I want to do? Do I want to do a left tail, a two tail, or right tail? And the alternative hypothesis tells me that. So what was my alternative? My alternative from the question was less than. Less than is to the left. So we think BMCC students are less than. If you choose the wrong test, you get weird results that are not easy to use, impossible to use. All right, so I select left tail, and then I plug in the number from my sample. So my sample said the average is 2.83. So I go down here to the x-axis, put in the 2.83. Okay. Oh, what does that mean? That's off the chart. Whoa. Okay, I'm going to attempt to draw a picture of this. Interesting. New page. All right, so by hand sketch of this, I draw an x-axis. I draw my best symmetric bell-shaped curve. It's not too bad today. I draw a line down the middle to say, hey, here's the population null hypothesis, 4.5. From there, I want to place the sample data. And you got to check with StatKey about where is it. So how far to the left should 2.8 be? Is 2.8 about here, or is it way out here? And so reflecting back the StatKey, it was way the heck out there. Okay, good to know. So way out here, and let's put that in red. This is my X bar, 2.831. And think about the, the two standard deviation rule. Two standard deviations would be about here, and 95% lives in that range, right? So that leaves 2.5% to live out in this range here, and I'm way the heck out at the edge of that 2%. And according to StatKey, the chance of finding another sample this small or smaller, that's called a p-value. That is 0. StatKey can't even measure it. It didn't find any resamples of that. And what is a p-value? So this is a big thing. It's talked about in sections 1, 2, 3, 4, and they get into a little more detail about it as the book moves on. So a p-value is a probability assuming the null hypothesis is true. So that's this assumption. That's in a conditional probability. So in probability notation, it would be, what's the probability of finding a sample where the mean is less than 2.83. Actually, it's 2.83 or less. That's not a huge deal, though. knowing if this is supposed to be the true mean of, we expect that to happen, and we expect X bar to be 4.5. And StatKey says, I can't measure that. Now, it could be I run another simulation and they will find one in there, 1 out of maybe 7,000, which is going to be a pretty darn small chance. So just for fun, I'm going to just let StatKey redo it. Because every time you redo this, you're going to get slightly different things because we're rolling the dice every time. Okay, so Tammy's was 0 as well. And again, this is a good thing to practice because this is how you're going to do your homework. So I want to just reset. And again, you don't have to change anything else. The data is still there, the mean's still there, just ditch the resampling. So I just generate thousands of more samples, and I got a pretty low one there, but it's really not. What is that at? That is a 3.35, right? So 2.8 ain't even coming up on the radar. So what StatKey is telling us, if you look at groups of 40 statistics students at a time, and you expect their average to be 4.5, the chance of finding this much less than 4.5, 2.8 compared to 4.5, that shouldn't happen by random chance. Okay, that's what we're hearing here. So again, to get that p-value, which is the chance of getting another sample like this mean, when we thought the mean was going to be around 4.5, that's the probability we're getting. 2.831 is our data, and it's 0 again. And my guess is if I run this 100 more times, I'm still going to get 0. Maybe once it'll come out to 0.000001. So what does this mean? This is the chance of finding another sample of 40 students with a mean TV hours per day 2.831 or less, when we were expecting a mean of about 4.5 hours per day. So this is the chance of finding another sample like this, assuming the null hypothesis is true. So the way the hypothesis test works is I have to get my data and plug it in. So perhaps you missed that part of the class. So the first thing I did when I got to the StatKey randomization test is I pasted in my data. Once I paste in my data, then StatKey tells me this is my sample statistic there. So that's the sample mean. And once I have the sample mean and I set the null hypothesis, I generate to run the hypothesis test. Choose the correct tail. Plug in that sample data that StatKey gave us. Mean is 2.831. And we'll do another one like this in a minute. So again, I still get a p-value of 0. So p-value is the probability of getting another sample like this or more extreme when we were expecting the null hypothesis to be true. So that one of two things happened here then. Either I have just a weird sample happened, you guys are just unusual compared to the rest of statistics students, or there's something wrong with my assumption about the null hypothesis. Expecting stat students, BMCC stat students, to watch the same amount of TV as the average adult is not a reasonable assumption. That null hypothesis is incorrect. So this right here, if I have a good sample, supports the alternative hypothesis. So this is evidence against the null hypothesis. And in favor of the alternative. And in statistics, when we look at something like this, we have a decision and a conclusion. So my decision here is to reject the null hypothesis. Either you reject the null hypothesis or you fail to reject it. And generally, we don't just accept it, but we say, well, the data supports the null hypothesis. In this case, we're just failing to reject it. So that's my decision. It's either reject the null or fail to reject. The conclusion then is basically a sentence that supports the alternative. So conclusion. Yeah, and my data is questionable, right? So I didn't go out and watch you watch TV. It was self-reported. Somebody may have mistyped something, right? So there's all kinds of problems with my sample. So let's forget about that for a second. Let's make believe I got a good sample. But I don't think it's actually that bad. I've done this many, many times before in a lot of different classes. And on average, college students seem to watch much less TV than the national average, significantly less than 4.5, even though some people tend to watch a lot and still survive. So conclusion here. There is sufficient evidence that BMCC statistics students watch less than 4.5 hours per day of TV type stuff. So whenever I write my conclusion, I don't want to mention the word null. I don't usually even mention the word alternative. I just try and state it like I was putting out a press release. And can I say that on average, all BMCC statistics students watch 2.83 hours per day? The answer is no, I can't. I could run a confidence interval and give you a range of values based on this data, but all the hypothesis test says is there evidence that they watch less TV or is there not evidence? That's it, right? And here I found, yeah, there is evidence that they watch less than 4.5 hours per day. That's all we got. Now, could I have made a mistake here? The answer is, yeah, I could have made a mistake here. I could be wrong about this. It could be that BMCC students really do watch about 4.5 hours per day. I just got a weird sample. And making that kind of error, so again, what kind of error am I making? That's kind of like a false positive. Like I went and got a COVID test. They said, oh, I'm sorry you got COVID, but I really don't. I'm fine. There's nothing wrong with me. So this could be a false positive. Talked about false positive test results back in the probability chapter. And I call this a false positive because I was looking for evidence that BMCC watched less, just like somebody might be looking to see if I have COVID, and they found, oh, look, there's evidence of it. But it could be wrong, which means it's a false positive. A false positive test result like this in hypothesis test is called a type 1 error. And we estimate the probability of this with a number called a significance level. So we estimate the chance of making such an error introducing a few new ideas right now that we didn't go over last time. So we estimate the chance of making an error like this. I should say type 1 error to be more precise. With a significance level. The significance level is given the symbol alpha. So that sucker right there is the lowercase Greek alpha. See this pop up in the book, starting in section 3, I think it is. And the usual alpha is that 95% rule versus 5%. So usually, which is what we did last time, alpha is 5%. So 0.05, oops, too many zeros, or 5%. And that's kind of based on the 95% rule. We say, okay, 95%, this is the usual range of stuff that can happen. If something happens in the upper or lower 5%, or maybe we split it, that's weird, then we gotta start asking questions. So that's where the 5% comes from. So this is not, it's important, but not that important. It's not life-threatening, but if you watch TV too much, that could make your grades suffer. So the people that end up in, say, 200 level math courses are the ones that don't watch a lot of TV because they pay attention, more attention to school. And then there's all those other things in our lives, right? But 5% is the usual one. So we estimate here there's a 5% chance I just made a mistake by saying that I believe BMCC stat students watch less than 4.5 hours of TV per day. And the significance level comes up in two places. One, to estimate that error, and two, it gives us a benchmark to decide whether our sample is unusual or not. So deciding if results are significant. So that's where alpha comes in. If your p-value, right, that's the probability we generated back here in StatKey, if that is less than alpha, then we say, whoa, that's weird, we better pay attention to this. So this would be reject the null hypothesis. Harley's brother doesn't watch TV and he's good in math. I don't know if there's an association between not watching much TV and good in math. When I was a kid, I watched way too much TV. And then I got to college and I realized I had to stop watching TV. I never liked video games. I wasn't good at math until college. Interesting. I don't know, maybe. P-value, oh, that's interesting. I'll have to write that down and think about it some more. Maybe there's data out there. Reject the null if this is the case. Sorry for that distraction there, it was a good comment. And if the p-value is greater, then we fail to reject. So just a note on that, and I'll do an example of it in a second. If we say, okay, we've got this null hypothesis here, it's right there. And then we collect the sample data and we run our hypothesis test, and the sample data ends up being like right here. So this would be my X bar. Then the chance of this X bar happening, if the null is supposed to be true, is pretty big. Maybe this comes out to be 40% for the p-value. What that means is there's a 40% chance of getting another sample like that when you expected to have this mean instead. Well, that can occur often. It's no big deal. That means our data is very much like what was the prior knowledge, in which case we say, I don't have evidence that the null is not true. Do I say I'm supporting the null? No, I just have evidence that supports it. Right? I could choose to come up with a statement. That's another interesting thing. When research is published about stuff, they tend to only publish the research where they had a very small p-value saying, hey, this is significant. But the research, when the p-value was the same, doesn't get published as much. So there is some research bias about this stuff right here. The book talks about that a little bit in sections 4.4 and section 4.5. It's a tough thing to wrestle with in terms of, in science, right, we're supposed to replicate stuff. And so if somebody says something is true, when we run another study to see if they're right, and we find it's true too, people just say, oh, it's true, okay, never mind, no big deal. And so that research doesn't get published as much is what tends to happen. But anyway, we're not always gonna pick 5%. It depends on the circumstances. And so we'll look at a couple of those in a sec too. New problem.